Today we're going to discover the connection between waves and energy, and how you can create a wave to transfer the energy from one location to another location for that matter. Now, wave cannot transfer mass, it can only transfer the energy and the information. How can you create a wave? It's very simple to create a wave. You can take a slinky, and if you move it up and down, you can create a transversal wave. Or you can take of course a slinky and move it back and forth, you can create a longitudinal wave. Alright, so it's time to divide the wave. So when we divide the wave, we divide it in mechanical wave and transversal wave and EM waves, electromagnetic wave. Mechanical waves need medium. Electromagnetic waves does not need medium. We can divide mechanical waves two parts. There are two types of mechanical waves. In fact, today we're going to go over the mechanical waves, and tomorrow we're going to go over the electromagnetic waves. Okay, so let's go over the mechanical wave. And one is longitudinal. Longitudinal, so let's use a slinky. So let's take a slinky and draw the longitudinal wave. So all right, so this is a slinky. You move it back and forth and you create a longitudinal wave. This is a slinky. You move it up and down and you create a transversal wave. You move it up and down. Move it up and down like this, and move it back and forth like this. Okay, good. Now, few things. This is crest. This is trough. This is called compression. This is called rarefaction. And this is called rarefaction. Okay, good. Now, we want to understand this one in terms of, let's say, the diagram. So let's draw a diagram. And this is high pressure. This is also high pressure. So compression is high pressure and rarefaction is low pressure. So this is the rarefaction, is low pressure. This is compression. This is high pressure. Now, In the transversal wave, the particle moves perpendicular with respect particle moves perpendicular with respect to the motion of the wave. Okay, so particle moves perpendicular with respect to the motion of the wave. In this, particle moves parallel with respect to the motion of the wave. Okay. Now here, how many cycle? You have cycle from this point to this point. You have one cycle, 1.5 cycle. You want to understand this one in terms of this, the transversal, we can definitely do that. So this would be, we're going to start it from here. So this is a high pressure, this is a low pressure, this is a high pressure again, this is a low pressure. Call crest or compression. This one we can call trough or rarefaction. Okay, good. Now, one more thing. Let me give you another wave. Okay, so now I want you to find, so let's say the length of the rope is 6 meters. I want you to find the wavelength. So length of the rope is of course 6 meters. I want you to find the wavelength. Length of the rope is 6 meters. I want you to find the wavelength. This is wave A and this is wave B. Wave A, the wavelength would be distance over cycle, and distance is how much we said? 6, and cycle is 1.5. This is one cycle, 1.5. So the lambda is 4 meters, and this one lambda is distance over cycle. Distance is 6, and cycle is 1, 2, 3 cycle. So this is 1 cycle, this is 2 cycle, this is 3 cycle. So 2 meters. Okay. So this is the lambda. So lambda is the wavelength. This is called amplitude. This is amplitude, and from trough to trough is lambda, or from crest to crest is lambda, from trough to trough is also a lambda wavelength. Some case study. So an example of mechanical transversal wave would be water. The example of mechanical longitudinal wave would be sound. All right, now let's take a look at the water. So when we talk about water wave, we actually divided it in two parts. The shallow and the deep. What makes it shallow water? Distance over lambda. If it is less than 0.05, then this is a shallow water. If the distance of a lambda is greater than 0.5, then it is what do you call the deep water. Now let's give you two examples. Let's say this is shallow, and let's say this is a deep water wave. Now the lambda over here, this is crest to crest is lambda, and this is of course the distance, the deep. Alright, so the deep is, let's say the deepness is 0.9 meter, and the deepness over here, let's say 60 meters. Okay, and the period is 8 seconds, and the period is 8 seconds. Now let me see the equation. The equation is lambda is equal to g t square over 2 pi. The lambda is equal to g dt. Now let's calculate lambda quickly. G is 10, t is 80 square, which is 64. 2 times 3.14 is 6.28. All right, now what do you have? 640 divided by 6.28, which is 99. Let's calculate it over here. Lambda, you have g, which is 10, d, which is 0.9, t, which is 8. So you have, let's say this is 1, so square root of 10, this is square root of 10, square root of 10 is 3 times 8 is 24. Okay, all right. So now let's see whether this is actually satisfy, this one is satisfy as shallow water. If it does satisfy the shallow water, then we're going to use the equation to find the velocity. Our goal is to find the velocity of water. That's what our goal is, to find the velocity of the water. Okay, good. Now what would be the equation? The equation would be lambda is equal to gd t. We know velocity is lambda times f. So lambda is gd, and f, and there is a t, and f is 1 over t. So tt cancel. So velocity is gd. Let's see this one. Velocity is lambda times f. Lambda is this one, gt square over 2 pi, and f is 1 over t. T goes to t squared t times. So the velocity is gt over 2 pi. Now, how do we know this is shallow water? If it is shallow water, then we're going to use this equation. Or let's verify. D is 0.9. So D is 0.9. Lambda is 24. So 24. And that is less than 0.5. Yes. So this is a shallow water. So we can find the velocity. G is 10, D is 0.9. All right. So 10 times 1 is almost 10. And then this is velocity is 3 meters per second. Because the square root of 9 is, this is actually 9. So the square root of 9 is 3. Okay, good. Now this one is, G is, let's verify whether this satisfies D force. So you have D, which is 60, and lambda, which is 99, and that is bigger than 0.5. How? Well, if this one is 100, okay, so 0, 0 cancel, so it's bigger than 0.5, obvious. So then find the velocity. G is, of course, 10, T is 8. Right, now we're going to do is speed of sound in the air. So speed of sound in the air. Okay. If you do speed of sound in the air, let's see what air made of. Air made of three types of so 1 2 3 nitrogen gas, oxygen gas, and argon. So nitrogen gas, how much percent? 78%, oxygen gas 21%, and argon 1%. Now what would be the equation? The equation to find out the velocity of the speed of sound in the air would be gas capacity, gas constant, temperature over molar mass. So now what would be the equation for molar mass? Molar mass would be nitrogen gas percent plus oxygen gas percent plus argon percent. Now nitrogen gas, we have to know the atomic mass of nitrogen gas. So how can we find the atomic mass? Atomic mass is equal to number of proton plus neutron. Now if you list all the elements from hydrogen to argon, let's see what happened. Hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. Okay, and then you have a sodium, you have a magnesium, you have a aluminum, you have silicon, you have phosphorus, you have sulfur, you have chlorine, and you have argon. Okay, so what do we have here? We have nitrogen, and we have oxygen, and we have argon. Okay, now let's see the number of proton in nitrogen is 1 2 3 4 5 6 7. It is 7 on the periodic table. This is 8 on the periodic table, and this is 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18. This is 18 on the periodic table. Okay, so atomic mass for nitrogen would be 7 plus 7, 14. How many nitrogen? 2. So times 2, 28. So I have 28 times 78 plus oxygen. Oxygen atomic mass. Oxygen is 8. So 8 plus 8 times 2, 32. So this is 32, and what percent is 21%. Plus argon. How many proton in the argon? 18. Neutron is 22 because argon is isotope. So you have 40 times 0.01. If you do the math, you get molar mass is 28.96 gram over mole. Now gram is not SI unit, we have to convert it to kilogram so that it is SI unit. So we divide by 100, so we're gonna divide it by 1000, so to convert it to the kilogram. So it's gonna be, if you divide it by 1000, that's 0.0289 kilogram per mole. Now we're done, almost done. So now we're gonna plug it to the equation. So C is 1.4, R is heat constant, T is let's say the room temperature right now is 20 degrees Celsius. So I have to convert it to the Kelvin. So 20 times 273, so 293. Divide by 0.0289 square root. So if you calculate this is going to give you 343. However, your reference table going to give you something different. Your reference table going to probably give you this one, 331 meter per second. Well, this is at 0 degree temperature, but at 20 degree temperature or at any degree temperature, how can you find it? Velocity of sound in the air would be 331 plus T in Celsius. So let's verify this. 1 plus 0.6, we use 20 degrees Celsius, so 20. So B is 331 plus 12, so velocity is 343 meter per second. So this equation will allow you to find the velocity of speed of sound at any degree temperature. Tomorrow we're going to do electric waves.